קישור במודל. אני אבדוק את זה.
יכול להיות שלא בדקתי כאילו ממש עכשיו.
הסרטונים יש של הקורס? אין במודל.
במודל שמתי קישור, נכון?
אני ראיתי את ה-22, אני לא יודע אם של השבוע יש עדיין.
יש קישור ליוטיוב, זה הכל מופיע ביוטיוב.
שמת קישור לסרטונים של שנה שעברה, התמדתי שנה זה לא מצולם?
שמתי ששנה שעברה. אני אבדוק את זה. חשבתי שזה של השנה.
לא, זה יכול להיות שזה.
זה נראה לי של השנה. כן, כי הקלטתי בעצם.
lascia domattina.
Yeah, I'm not having, not that we are.
יכול להיות עד סוף השבוע. יהיה פרסם מאוד.
Là, on fait des simulations, et après, c'est que, en gros, ensemble, il y a tout bien. Ah, mais. Alors là, on passe.
Avec grand plaisir, il y a tellement de réactions que ça veut dire. On recrutait vraiment ensemble aussi.
Je veux bien recruter avec toi. Non, mais comme ça, justement, comme il y a peu, tu vois, on peut dire, ok, chef taf, protocole, ADN, jeu plasmide.
C'est quoi? La photooptique, on va prendre un exemple parce que tu connais pas moi.
Sur quoi?
En optique.
Ah, il y a pas peu avec ça. Il y a
Ouais,
peu, il y a la.
ouais, optique et il y a l'autre.
Et optique, c'est facile.
Je pense que c'est un truc qu'on a fait pour.
Bon, de toute façon, on a fait tout ensemble avec.
Ouais.
Non, on est ensemble.
On a juste à 2 heures de rendez-vous après pour dire pour faire un petit histogramme du classium type pour qu'on s'imagine les points.
Okay, welcome back. All right, so I promised you a continuation to the topic from last week, where we're going to look to generalize it or put it in a more general, broad linear algebra context. So what we saw last week was we had a question about amplification. We want to be able to, with a linear network, have a rapid amplification of a signal, and we saw that it looked like, just from a naive eigenbasis decomposition, that we'd be forced into a trade-off between amplification and speed. But then we saw that that's not exactly the case, and we had this example network of just E and I, two neurons, with strong inhibition, and we analyzed that system in a few different ways. We had the schematic picture of E and I. We looked in the eigenbasis, and we saw two negative eigenvalues. So we thought maybe we would just have decay or small amplification, no amplification. But then we saw that there's a different basis that we could look at. We could turn to, we saw that our eigenvectors were overlapping. They were non-orthogonal eigenvectors. And that gave us, so that the eigenbasis gave us a kind of distorted picture of the overall dynamics, even though in the eigenbasis there would just be a decay of the dynamics from an initial condition. If we looked at the actual standard basis of Re and Ri, we could see an initial transient amplification of the dynamics, a rise in the activity of both neurons, as shown here. both RE and RI rising. And we saw that we could understand that through this other basis, which was a unitary or orthogonal basis. And in that basis, our connectivity matrix was upper triangular. And that structure, schematically, meant that we have two modes. In this particular case, a difference mode, the difference between E and I, and sum mode, the sum of them. And we saw that essentially the way the network behaves is as if the difference mode is providing feed-forward input into the sum mode. So even though both of them intrinsically have simple decays, if we start off the network and give it a bump in the difference mode, so make RE and RI very different from one another, then effectively we'll have a potentially very strong feed-forward drive into the sum of RE and RI. In such a way that we can have both a strong amplification without slowing down. Okay, so now I want to talk about this basis. So this isn't just an arbitrary, very specific basis. This basis is an example of a broader phenomenon, and it's called the Shor basis, or the Shor decomposition. So the Shor decomposition, Lior, who's writing up the notes, writing up the textbook for the course, while preparing this section, he found out that Shor is actually buried in Tel Aviv. So if you're totally amazed by this decomposition, you can go show your respect and visit. So the Shor decomposition, and now. So there's a theorem, the Shor theorem. And it says that the theorem basically says that what we saw here, this particular basis that's a unitary or orthogonal basis, and turns our matrix into upper triangular or lower triangular, that's a very general result. And that every square matrix has such a basis. For every square matrix W, there exists a unitary or orthonormal, orthogonal matrix U, such that we can write W equals U T U inverse or U conjugate transpose, which are equivalent, right? Because we have the unitary condition just means that U inverse is equal to U conjugate transpose. So every square matrix has such a basis U, under which it's and I didn't say about T, and that T, we can write it either way. Even though we had that as upper triangular, we're going to go with the convention of lower triangular, such that U is unitary and T is lower triangular. But it's really just a convention, which side you choose. So T is lower triangular, and additionally, the diagonal elements, the elements along the diagonal of T, are the eigenvalues of W. And so here we saw an example of that. Along the diagonal, we have the same eigenvalues, 0 and minus j plus. And so this tells us that W written in the basis of U is just equal to T. and that has lambda, the eigenvalues, on the diagonal. It's 0 above the diagonal, and it has some lower strictly lower triangular elements potentially below the diagonal. Okay, so this is a very, very general. Every single square matrix you give me has this form. And like I was saying last week, the fact that this matrix is unitary is important because we know then when we change basis into this picture, we haven't distorted the dynamics in the same way that we saw that the eigenvectors did. In this basis, the norm of the dynamics is the same, whether we're looking in the original basis or whether we're looking relative to the Schur basis. So we have this matrix U. The columns of U, call them the Schur modes. And if I have some vector R that I want to write relative to this basis, so the decomposition of the U over the modes with some coefficients, call them Sk. So that's like writing the matrix U times Sk. So as we saw, one of the crucial features of a unitary basis is that if we take R transpose R, which is the norm of R, it's going to be, sorry, this isn't Sk, this is S vector. Right, that's the vector of components S. So we know, as we saw last week, that the norm of R is basically preserved under this transformation because we have S vector transpose U S, which is just S transpose S. Now, furthermore, now we have that the interactions between S have this form, have this lower triangular form. So what does this lower triangular form tell us? So it tells us, in essence, if we look at this schematically, we have S1, which has its own self-coupling lambda 1, and it also can project to S2 and potentially down the line. And we have S2 with its own coupling, and then potentially can project forward. And then we have finally at the end of the chain we have Sn, which only projects to itself through lambda n, but it doesn't send any feedback back up the chain. And so this is the generalization of the schematic that we drew over here, where our two neuron network could be seen as a effectively feed-forward chain of two modes, one projecting to the next, and then the other one just giving to itself. So that turns out to be true for any square matrix that has this form, where it can be seen as a feed-forward chain.
Well, did you write the eigenvalues as a self-connection? As a self-connection as all the lambda?
Yeah. Why did I have those?
Because it's the diagonal.
Yeah, so the eigenvalues, the original eigenvalues of W are ensured to be the diagonal elements of T. Right, so that if we're writing, what I'm doing is taking S dot equals T S. And then what I find is this picture. Okay, so let's see that. So basically, we have here lambda 1, and then lambda 2, and then this can be T1, 2, and so on. So we can see right, just doing this multiplication, S1 dot is just equal to lambda 1 S1. S2 dot, it has lambda 2 S2, but it also has T1, 2, T2, 1 would be the usual way of writing this. T2, 1, sorry, miswriting everything. So S2 dot is equal to lambda 2 S2 plus T2, 1 S1. Right? And we can go on at least one more step. Lambda 3. We have S3 dot has lambda 3 S3 plus T31 S1 plus T32 S2, and so on. Right? So that the elements under the diagonal are these feed-forward projections. So also, as we discussed last week, obviously the eigenvector composition is the most useful algebraically, because then we can solve any of the particular components totally independently of all the rest. And we give that kind of luxury up if we use the Schur basis. But we still have a way in which we can solve this. We can solve this iteratively, kind of going up the chain, right? Or going through these equations one at a time. So we can solve these one at a time, starting from the top of the chain. Right, S of 1 is just S of 1 times 0, e to the lambda 1t. And then we use that as input to solve S of 2. Right? Okay, so given that this is a very, very general universal statement, it's a little bit surprising that not everybody has heard about the Schur decomposition. You don't learn it in linear algebra, and a lot of people, even who are like doing a lot of math, a lot of linear algebra, a lot of dynamics, haven't even necessarily heard of the Schur decomposition. And so one reason for that is that this is a true statement, but a lot of times this t lower just doesn't exist. A lot of times it's 0. So when is that the case? So let's see. First of all, let's say what if t lower is 0? Then what do we have? We have w equals u lambda 1 lambda n with zeros now on both sides, and u conjugate transpose, which is again equal to u inverse. So what do we have here? This is now just the eigenbasis. Right, so in the case where t lower is 0, then u is actually the eigenbase. So in that case, they're identical. The Shor decomposition is just the eigen decomposition. And now, obviously, it goes in the other direction, right? If U, an orthonormal or a unitary matrix, is an eigenbasis, then we can write this, and the matrix in the middle is naturally lower triangular, but with the lower part being 0. So these conditions are equivalent, and the set of matrices that satisfy that condition are called normal matrices. And that's an important class of matrices to be familiar with. And in physics, almost all matrices that you come across are normal matrices. So physicists are used to seeing the eigenvectors, eigenbasis as almost always being orthogonal, being a unitary matrix. Now, the strict definition of a normal matrix is a matrix that satisfies W transpose equals W transpose W. That's the formal definition.
But it doesn't necessarily have to be one, like I, right?
No, that's restricted to unitary, yeah, orthogonal. So it's a broader class, but right, we can notice that unitary matrices are a subclass of normal matrices, because if we have a unitary or an orthogonal matrix, then we just have the identity here, and obviously in that case it can go in either direction. And I won't prove this, although it's not too difficult to prove. Well, to prove what? So first of all, normal matrices have orthogonal eigenvectors, orthonormal unitary eigenbasis. But probably the most important fact to get in that direction, so the necessary lemma, as they call it in math, is that a general fact for matrices is that if we have matrices A and B such that AB equals BA, then they share eigenvectors. They have this. One has to be a little bit careful, but if these are matrices with n discrete eigenvectors, then they have all the same eigenvectors. The general statement is that they at least share some eigenvectors. If AB is equal, if they commute, so matrices that commute have the same set of eigenvectors. Same eigenvectors. Right. Yeah, and so this is a restricted class of matrices. The matrix that we saw last week, so if you recall, the two eigenvectors last week were P1 and P2. So those are not orthogonal, right? We had P1 is just 1, 1, and P2 is something like J, I, J, E, which were not orthogonal, right? So crucially, the matrix that we looked at last week was non-normal, so it didn't satisfy the situation. But yeah, so this is a lemma towards proving this fact. So what we know from this is that a matrix that is normal, W and W transpose or conjugate transpose, have the same set of eigenvectors. And so if that's the case, if they have the same set of eigenvectors, then it turns out to be the case that the eigenvectors themselves are orthogonal to one another, and that the Schur decomposition then is just the trivial, it's just the eigenvector decomposition. So in that case, we don't care about the Schur decomposition, and we also, in the case of a normal matrix, then we don't have this form of feed forward, right? Because all of these feed forward links in the chain, the lower triangular part is just all 0. So a normal matrix has no feed forward structure. No feed forward structure. And so if you have a normal matrix, then you can just totally rely on the eigenvalues, and they'll give you a fully intuitive picture of what's going on. And we know that because the eigenbasis, the eigenvectors are orthogonal, and you can have a unitary eigenbasis, so that the rotation to the eigenbasis is just a pure rotation and doesn't distort any of the directions. So that in that case, you can be fully content with just going to this decomposition eigenvectors. It's going to be identical to the Schur ones. You don't have to know about the identity of the particular eigenvectors in order to have an intuitive picture of what goes on in the dynamics. But any non-normal matrix, then you need to know more information than just the eigenvalues themselves, because the eigenvectors will not be orthogonal, and they'll have some kind of overlap, and the Schur decomposition will have some non-zero lower triangular structure, and schematically will have some kind of feed forward structure. Okay, so we have this general fact. Normal matrices don't have an interesting feed forward structure, and non-normal matrices do have some kind of feed forward structure. But is that of interest to us? I mean, we've seen one case in which the matrix that we had, the 2x2 matrix, was non-normal, and it had a hidden feed forward structure. But is that of interest more generally? So it turns out that there's good reason to think that it is. So let's look at biological connectivity matrices. And by biological in this case, I really mean what's referred to as Dale's law. Dale's law just means that a neuron is either excitatory or inhibitory, all of its projections. And that's maybe not universally true in the real world, but almost. So a connectivity matrix that satisfies Dale's law looks like this. We can subdivide the matrix into sub-blocks. A JEE block, minus JEI block, JIE block, and a minus JII block, where all of the elements in these submatrices are all positive. Right, so we can look at the signs of the submatrices, plus plus, minus minus. And now ask a simple question: is this matrix can this matrix be a normal matrix? So let's look at J transpose, and this would be a very large matrix, so obviously not going to calculate the full matrix, but we're just going to look at the signs of each quadrant, the signs of the submatrices. So if we take J transpose, we have plus minus times the transpose, which is plus minus minus. Right? Every element in each of these quadrants, in this quadrant is plus, every element in here is minus. So let's look what happens when we multiply it. We have this whole positive quadrant times this whole positive quadrant, and the negative quadrant times the negative quadrant, that's also positive. So here we get positive, right? Again, we have the same thing here. Plus times plus and minus times minus gives plus. Here we have plus, right? Basically everywhere we have plus times minus, or plus times plus, and then minus times minus. So JJ transpose is positive everywhere. What about J transpose J? So here we switch the order. We have plus, plus, minus, minus, times plus, minus, plus, minus. Okay, so now we have plus times plus and plus times plus in the top left. But then we have plus times minus and plus times minus over here in the top right. So that's necessarily negative. In the bottom left also we have minus times plus and minus times plus, which is necessarily negative. And then finally we have minus times minus and minus times minus, which is necessarily positive. So what we have is for sure J transpose does not equal J transpose J. So we have a very simple proof that any matrix that satisfies Dale's law is non-normal. If it's non-normal, then the eigenvectors are not orthogonal, and the Shor decomposition has a lower triangular matrix with non-trivial lower triangular part, and there's some kind of feed-forward structure that's hidden in the matrix. So that's a very interesting and broadly relevant fact. But it's important to ask also, to what extent? So can we also give a measure of normality or non-normality? So we said this is not normal, but is there a sense in which we can say even, is it even meaningful to ask, is it close to normal, is it far from normal? I think there's a whole literature of math research defining normality and measures of normality, so I think there's lots of different ways to do it. But I'll just show you one here, a measure of non-normality. So, an important fact about the Shor decomposition is that this form is not unique, which is not like the eigenbasis, right? The eigenbasis is unique up to, I mean, you can reorder the vectors, or you can scale them differently, but the directions that are the eigenvectors, those are the eigenvectors. The Shor modes, these columns of U, those are not unique. So if I found one basis, in our specific case, I wrote one basis, it was the plus mode and the minus mode, sum mode and the difference mode, that gave us upper triangular. It turns out I could have chosen a different basis that would also give me upper triangular. So the actual basis vectors, the Shor modes, are not unique, and that means that we can have different lower triangular forms. What's on the diagonal is obviously unique because what's on the diagonal is the eigenvalues. So those are given. You have a matrix that's got eigenvalues. But what's below the diagonal, it turns out, can differ by your choice of U. There's not a unique choice for that. But what is preserved, no matter what choice of U you take, it turns out that the sum of the squares of the matrix T, that is preserved. The sum of squares of the matrix is preserved, it turns out, under any unitary transformation. under any choice of U. And it's equal to the sum of the squares of the original of the original matrix. Turns out another way to write this is as the trace. So we can look at the original matrix, the trace of W transpose. So why is that? Why is the trace of this equal to the sum of squares? If we look at WW transpose along the diagonal, II, so WW transpose we can write as sum over, or the ith element is equal to the sum over J of Wij times Ji, W transpose Ji. But W transpose Ji is just equal, again, it's just equal to Wij with a complex conjugate if we allow complex. So this is even true beyond real matrices. That doesn't necessarily interest us, but that shows that the ith element of WW transpose is the sum over J of Wij squared. And so then if we take the trace is just the sum over the diagonals. This is equal to the sum of squares of the whole matrix. And a useful fact, the fact that I'm not going to prove, is that the sum of squares of a matrix is preserved under a unitary transformation. So why am I going through all of that, these linear algebra facts? Again, it's to try to give us a measure of non-normality. So we have this decomposition into the eigenvalues on the diagonal and some lower triangular part of the matrix. And what I said is that it's not unique. I can have a different lower triangular matrix, but the sum of the squares will be preserved. So one useful measure of normality is to say, well, how much of the sum of squares is just composed of the eigenvalues, and how much is from this lower triangular part? And that is a well-defined measure in the sense that it doesn't matter which basis I choose, which Shor basis I choose, that measure is well-defined. So the fraction FW of the sum of squares that is in the lower triangular part. So I can write it as basically the sum of squares of the full matrix, Cij, minus the sum of squares of the eigenvalues. I guess I should put that divided by the full sum of squares. That's a fraction of kind of power of the matrix that is in the lower triangular part, or is in the effectively feed-forward part of the matrix. And another way to write that is as the trace of W transpose minus the sum of the eigenvalues squared divided by just the trace of WW transpose.
I is equal to J in each one of these cases, right? I is equal to J.
Here?
This is a scalar.
In Ti.
Yeah, because you're just summing the square root.
I'm summing over all I and j. right? For the full matrix T. Yeah, in this case there's only one sum, so it's sum over J. But when I write this, I mean a sum over I and J of all the elements of T, all the elements, each of the elements squared. Okay, maybe in a homework exercise, you get to apply this to see to what extent a typical biological connectivity matrix, or maybe the example that we saw. In the example that we saw, we had something like minus J plus and then JFF 0, 0. If we flip the order, we can make this lower triangular, just flip the order of the basis vectors. And so what we saw last week was that if we chose to make both JE and JI very large, but with a small difference between them, then J plus could be not so large and JFF could be very large. So in this case, we have a matrix that if we choose the parameters to be strongly inhibited, strongly but balanced inhibition, then we can have a case of a very, very non-normal matrix in the sense that the sum of squares could be really dominated by the off-diagonal component.
Is there a range for saying how not normal is it? I mean, if I get 0, say normal.
Right. So it goes from 0 to 1, right? So that's the scale, and so 0 is a normal matrix, and 1 is. So we saw a case actually of a matrix that has 1, and I'll just close with that. If you remember, in the last section when we were talking about working memory, Jonathan presented a form of working memory which was just a feed-forward chain, right? Jonathan's example of a delay line or feed-forward chain was this matrix that just had connections all along the one below the diagonal. And this was the feed-forward chain for working memory. Feed-forward working memory. And so in that matrix, all of the power is in the off diagonal. So that has FW is equal to 1. And I'll also note here that Jonathan closed by saying that, okay, this was a very particular form where each neuron projects to the very next neuron, but that you can take this J matrix and generalize that with U, J, U inverse, or U transpose, and that's exactly kind of using the Schur decomposition view of things to say we can have a matrix that on the face of it doesn't look like it's feed-forward. It appears to be recurrent in the same way that our 2-neuron matrix is really recurrent, but if we find the Schur basis, it turns out to have just a pure feed-forward structure. Okay, that is it. Jonathan will be here for the next hour to start the ring model. אפשר, זה תמיד אפשר לעבוד באייגן בייסיס, זה צור שיש דברים שאנחנו לא רואים שם, לא קוראים לראות אותם. אז זו שאלה טובה, מה שאולי לא כדאי לציין פה זה שגם ההשפעה יכולה להיות מאוד אחרת, גם בין גם בין צורה, מה שראינו בדוגמה הזאת, זה מעניין שהוא מהר, שהוא זה מה שרואים פה, זה משהו שהוא טרנזיאנט שהוא מאוד ארוך. זה כאילו מאוד שונה, זה יכול להיות מאוד נורמל, זה מאוד שונה.
En fait, de manière générale,
וכמה
chaque l'image de chaque, imaginons, là tu es dans la base B, et là tu es dans la base de C. Dans la base, qu'est-ce que tu vas y voir dans les collages? Tu vas y voir chaque vecteur dans la base B, et là tu vas avoir les coordonnées de l'image mais dans la base de C.
נראה לי שכבר בעין יש בזה תחושה שמשהו קורה שם ציפור, יש אקסיטציה שהולכת
en général, là c'est les c'est dans le cas un peu simple, général, enfin général justement en particulier dont on a l'habitude. Ça, là tu as les vecteurs élémentaires, okay. Et là c'est quoi vecteur? Ouais, mais c'est exprimé dans quelle base? Dans la base.
So from that, like we can think about it from the schematic picture before I erased all these other things. So
okay,
just tell us
donc c'est des eigenvecteurs.
it's a rough measure of overall power
in
these connections. How much of it is in the feed-forward part versus the overall? Versus the overall.
Qu'est-ce qui s'est passé? Dans U là, t'as
compared to the self.
Ouais,
effective self.
donc ça maintenant c'est le cas particulier. Maintenant si tu généralises de
Comment
manière
tu ça?
avec des billes,
Moi je colle résultat de quelle base?
De l'ancienne base.
Non.
De la nouvelle base.
שזה יכול להיות שבו
exprimé dans
אפס פה.
כמה ביחד או כמה זה פיפור? לא כל מה שאתם יכולים לאפיין אותה.
La matrice U, elle a des vecteurs polarisés. Dans le cas qu'on connaît, c'est quoi? C'est exprimé dans quelle base?
La base normale, la base de B.
Ouais, mais c'est-à-dire des 1, 0, 0.
La base élémentaire.
La base élémentaire. Ok, maintenant dans le cas général, U, c'est des vecteurs de quoi élémentaire? Si tu essayes d'appliquer par analogie,
donc B c'est la base élémentaire, c'est analogue à la base élémentaire. Donc c'est des vecteurs, je sais pas quoi.
Non, justement. Ouais, mais c'est quel vecteur? Bah ouais, mais regarde, qu'est-ce qui s'est passé là? Il y a quel vecteur là?
C'est les vecteurs de U.
Ouais, non, mais dans le cas des eigenvecteurs, il y a quel vecteur là?
L'eigenvecteur.
L'eigenvecteur, qu'est-ce que c'est l'eigenvecteur en termes de B?
Ça je l'en fais pas.
Bah, tu me dis qu'est-ce que c'est l'eigenvecteur. Quand on dit quoi? Exprimer dans?
L'eigenvecteur c'est la base.
De quelle base?
La nouvelle base.
La nouvelle base. On passe de quelle base à quelle base?
De la base élémentaire à l'eigenvecteur.
C'est ça. Donc de manière générale, t'as quoi dans A et t'as quoi dans U? Dans A.
Dans A, j'ai la transformation.
Ouais, donc mais ça veut dire que tu vas avoir quoi?
J'ai genre comme l'eigenvector. Non, j'ai l'eigenvector, mais...
Dis-moi U déjà.
U, j'ai l'eigenvector.
Ouais, mais... Non, mais maintenant de manière générale.
Ok,
quel
alors U, j'ai la nouvelle base.
C'est-à-dire écrit... ouais, exprimé dans quelle base?
La nouvelle dans l'ancienne base.
C'est ça. Donc dans B.
J'exprime genre 1.
Exprimé
B.
dans B.
Vecteur B. Prime N.
Exprimé dans B. C'est ça.
Donc, comme ça.
Et chacun, donc, ça va être une combinaison linéaire de B. Des vecteurs de B, c'est d'accord?
Chacun.
Chaque vecteur de la base B',
ouais.
c'est une combinaison linéaire des vecteurs. Est-ce que tu es d'accord en fait? On pourrait dire ça. Ça, c'est B'1, B'1, B'N.
Ouais.
Ça, c'est B1, Bn. D'accord? Dans la matrice U, qu'est-ce que tu as? Tu vas avoir, dans la matrice U, tu vas avoir B'1 exprimé dans B. Ensuite, donc ça c'est le vecteur colonne, et B'N exprimé dans B. Et qu'est-ce que c'est par exemple on prend un B' au hasard, une de ces colonnes.
Ouais, ok.
Disons, prenons B'J exprimé dans B. Ok, donc le JM.
Ouais.
Bah, qu'est-ce que c'est? Ça va être une combinaison linéaire de AJ dans la base. Dans quelle base? Dans la base BJ. Et comment tu peux écrire ce vecteur aussi? Tu peux dire que donc ça va être c'est une combinaison linéaire, ok.
Ok.
Ok. Donc, et en fait, quant à ça, c'est-à-dire que ça c'est quoi? Les AJ c'est quoi? C'est les coordonnées du vecteur des primes dans quelle base? Dans cette base. Donc ça veut dire que tu peux l'écrire comme A1, ça, A, N. Et donc ça, c'est donc les coordonnées du vecteur de prime J dans la base B, tu le mets où ça? Tu le mets dans ta matrice A, dans la JM ici, dans la JM colonne. Et tu fais pareil pour chacun, ok? Maintenant dans la matrice A, qu'est-ce que tu as?
C'est une matrice de base.
Non.
Mes vecteurs.
En
Ah,
fait,
c'est la matrice que j'ai exprimée dans une autre base maintenant. Ouais.
Ah ouais, donc qu'est-ce que c'est?
Avec mes coordonnées dans la base élémentaire. On a l'ancienne base.
Imaginons que tu as une base, ok?
Ouais.
Tu vas avoir une autre base. Toi, ce que tu aimerais, c'est tu as une application linéaire, donc ça veut dire que tu aimerais que...
Ah, c'est l'application linéaire elle-même.
A, c'est la matrice d'application linéaire, ok? Maintenant, le truc, c'est que tu aimerais dire, ok, cette matrice d'application linéaire, donc c'est des nombres, mais elle marche, donc elle est valable pour une certaine base, ok?
Ouais.
Donc ça veut dire, si je l'applique à un vecteur dont les coordonnées sont données dans une certaine base, alors je vais avoir l'image dont les coordonnées sont données dans une autre base, dans la même base, excuse-moi.
Ouais, toi tu
Tu vois ce que je veux dire?
Ouais, je vois en gros. Faut que je revoie le flow. Quand je comprends que tu dis, il faut que je revoie le flow avec la démonstration et tout.
Et donc ce que tu fais, c'est que quand tu as une matrice d'application dans le linéaire dans une certaine base, toi tu as un vecteur qui est exprimé dans une certaine base. Ok? Tu peux pas dire... parce que tu vois, on a dit que chaque matrice A, elle peut avoir... elle a plusieurs formes similaires. Enfin, en tout cas, la forme... ok. Tu peux pas dire je prends n'importe quelle matrice et je l'applique à ce vecteur pour l'application. Tu vois, une matrice, elle a des coefficients.
Ouais.
Qui vont multiplier chaque coordonnée. Tu vois, tu vas faire des combinaisons linéaires de chaque coordonnée des vecteurs, du vecteur exprimé dans une base. Mais cette matrice, elle est valable dans une base. Parce que si tu te mets dans une autre base, le vecteur, comment ça s'appelle, AX, c'est l'antécédent, c'est ça? Le X sur lequel tu vas appliquer la transformée, il est exprimé dans une certaine base. Donc si tu veux trouver la transformée de ce vecteur dans toujours cette base, non, ce que je veux dire c'est que tu vas avoir une certaine matrice. Maintenant si tu calcules le même vecteur mais dans une autre base, il va avoir des coordonnées différentes. Donc ça veut dire que la matrice d'application linéaire, elle va avoir aussi des valeurs différentes. Parce que tu vas pas faire les mêmes combinaisons linéaires des coefficients des coefficients du vecteur. C'est tout. Mais t'as compris ou...
Ouais, j'ai compris, c'est juste que là je peux pas te le répéter, parce que tu peux jouer avec ça mon avis plein de fois et te rappeler il n'y a rien de compliqué, c'est juste que c'est des trucs, tu sais, genre une gymnastique à faire rapidement à chaque fois.
Mais si tu l'exprimes une fois, genre au moins tu poses bien chaque vecteur exprimé dans quelle base, tu vois, c'est...
Ah ouais, je vais le faire ce soir.
En réel, c'est bien.
Why did I change in biology?
Yeah, dude. Fan, det var fint också.
C'est vraiment pourquoi tu veux pas aller cours pendant un lycée.
Jag har experimenterat.
Det låter som en kaka, va? Det låter som en kaka.
Nej, djursrörelse.
Ja, det var nästa.
La flemme.
Non, il est pas
Det är Aftonbladet som får det flera dagar sedan.
Jag ska inte få se.
C'est clair ou c'est...
Jag kan inte.
Honnêtement.
Okej.
Cette info oubliée, que nous on n'avait pas entretenir.
Ouais, c'est ça, non mais c'est pour ça, je sais.
C'est...
Ce que je veux savoir, c'est parce qu'on sait qu'en question, même là quand on regarde l'article, c'est toujours comme ça. On prend pas trop grand-chose. Est-ce que la question, t'as semble...
J'entends parfois la dire on l'a défini une fois, mais c'est quoi genre...
Ouais, mais le problème c'est que...
Jag har 3 millions.
c'est pas grave, hein, ça ne dépend pas que
Le fait que
non, non, mais ce que je veux dire,
vous avez parlé du sujet, vous avez défini, vous avez défini dans problématique.
si personne ne comprend rien, c'est-à-dire que
Non, mais c'est vas-y, on a compris, c'est pas j'ai compris de votre point.
ah, ça va? Ah, voilà.
C'est beaucoup, t'as pas tout.
Okay. So the topic of today's class is selectivity and the models for selectivity. With Itamar, you discussed methods for some ideas about. We can think about it as feed-forward or transient mechanisms for amplification. Today we will talk about amplification in the steady state, amplification in the attractor, different mechanism for amplification in the framework of selectivity. So if we look at the cortex, basically everything that we know about the cortex, or much of what we know about the cortex, is in experiments in which we use stimulus depending on the modality that we're interested in. We put an electrode, or in the past we used to put an electrode. Today we put either many electrodes, or we do calcium imaging and things like that, and we look at responses of individual neurons. And we find that basically all over the place, we find that neurons are selective for external variables. Often these are spatial variables. And the examples, primary visual cortex, MT, posterior parietal cortex, frontal eye field, motor cortex, entorhinal cortex. Well, that's not exactly the cortex, but we see similar things in the hippocampus. Basically, all over the place, we find selectivity for spatial variables. And this is very, very common in the brain. One of the best known examples, and one of the first examples, this is from the work of Hubel and Wiesel. So Hubel and Wiesel presented animals with stimuli, with moving gratings or moving bars, and they found that neurons in the primary visual cortex, in the occipital lobe, neurons are selective for orientation. This is presented in these examples. So this is a neuron that responds most when the bar moves in this. A bar of this orientation moves in this direction, and it doesn't respond much if this is orientation or if this is orientation. One way of quantifying it is to look at the find rate as a function of the orientation. This is a classical example. Any questions? Actually, we saw similar thing in the first class when we started to talk about why we care about spikes. This is another example, another classical work. This is from this is by Georgopoulos. This case, this is a recording from the motor cortex. These are rasters, and you have a monkey, and the monkey is trained to move a manipulandum to one of 8 directions. So these are the 8 directions. 8 directions. And what you see here are examples of experiments. This is the spike times when the monkey moves the manipulandum in different directions. And in this case, animal fired most when the monkey moves the manipulandum in this direction. And we can plot, well, Georgopoulos plotted the find rate as a function of the movement direction and got a similar bell curve, similar to what Hubel and Wiesel found in the visual cortex. other examples, these are head direction cells. These are cells that encode the direction of the head. So there are many such examples. Going back, looking at selectivity in the primary visual cortex in slightly more, what used to be more modern technique now is already almost obsolete. This is a map of orientation preference. This is a cortex, and these are preferred orientation of bars, and you see that different colors, so different colors correspond to preference of neurons to different orientations, and this is if I'm not mistaken, this is part of the primary visual cortex. So what we learned from this thing that was difficult to learn from this is the spatial distribution of the orientation selectivity. So you see that neurons nearby have similar preferred orientation, and there's some continuity of preference. For example, if we move from here to here to here to here to here, and here and then we see these singularities that are called pinwheels. Very interesting, but there's a lot of interesting research on these pinwheels, but we will not have time to discuss it. So these are just very classical and representative examples of selectivity in the cortex. And the question that people ask themselves, and have been asking for quite a while now, is how does this selectivity emerge? So historically, Hubel and Wiesel, interested in this orientation selectivity in the primary visual cortex, they came up with a mechanism that explained the emergence of selectivity by considering or thinking about the spatial organization of receptive fields in a feed-forward manner. And allow me to elaborate. So if we look at the retina, what is the spatial selectivity of photoreceptors in the retina? What's the shape of a receptive field of a photoreceptor in the retina? Do they care about faces? Do they care about stars? Do they care about, what do they care about? But spatially. We talk about photoreceptors in the retina. We have a retina. Just a location. So to a first approximation, you can think about photoreceptors in the retina as pixels on the screen, and if you have a photon that is hitting the photosensitive molecule, then it will cause a change, and if it doesn't, it will not cause a change. And basically, the spatial structure of the receptive field in the retina is circular. It's just corresponding to the small region in the space of directions from which this photoreceptor is selected. So the first approximation, this is what photoreceptors care about, just the location in measured as direction in space. Now if we move further, we look at the output ganglion cells in the retina. They have a slightly more it's known center surround receptive field. Basically, they either care about they're activated for inputs in the center of the receptive field and are inactivated for inputs that are slightly outside this focal point, or the opposite, but basically the receptive field looks something like this. They're circular. There is no spatial selectivity. But again, if we look at the primary visual cortex, suddenly neurons care about orientation. And the question how something that has that looks like this, how selectivity that looks like this, so you respond to inputs that are here, how does such a thing emerge from neurons that care about circles? So at least we know that in the retina they care more or less about, again, to first approximation, they care about circles. So what Hubel and Wiesel suggested is that the organization of input coming from the thalamus, coming from the LGN, the spatial organization of this input underlies this selectivity in the primary visual cortex. So this curve tells us that the neuron would respond to input that is here and to the absence of input here in the flank surface of this middle line. And they propose that the mechanism underlying the emergence of this selectivity in the primary visual cortex is the specific mapping of these circular receptive fields from the LGN to the primary visual cortex. So this is the idea. The idea was that spatial direction selectivity in primary visual cortex is a result of the feed-forward connections, the way that they are mapped into individual neurons in the primary visual cortex. Questions about this? Now this was the dominant view for several decades, but there are several problems with this view, and I'll just mention a few issues. One is the fact that neurons in the primary visual cortex, most of the input that they receive actually comes from other cortical neurons. More than 90% of the input to cortical neurons in the primary visual cortex comes from other cortical neurons in the primary visual cortex. So this feed-forward input is just a minority of the inputs. And this model completely ignores the recurrent connections. So we would like to understand what's the role of these recurrent connections in the formation of this selectivity. This is one issue. Another issue, which I think is rather interesting, so one thing that people noticed when they use this technique to look at large areas of the primary visual cortex. So how do you generate this map? So one way of doing it is to use something that's called voltage-sensitive dyes. These are dyes whose cutting a long story short, we are able to measure the response of large populations of neurons, and using optical imaging, and what you see is which are the regions in space that are activated most by different orientations. So you can do these experiments, but you can also look at the spontaneous activity. One can also look at the spontaneous activity in these brain regions in the absence of any visual input. And surprise, surprise, the evoked activity, the patterns of evoked activity are actually very similar to the patterns of spontaneous activity in the absence of any input. And this is consistent with the idea that most of the activity in the visual cortex is actually generated by other cortical neurons. So taken together, this feed-forward framework seems to be insufficient to explain anything that's going on in the visual cortex, and specifically the formation of orientation selectivity. So what we will do today, we will discuss the possible role of recurrent connections in the formation of. We will think about orientation selectivity, but basically we're thinking about, well, all these other examples, direction selectivity, and perhaps also things more that are also the formation of place cells and grid cells. So the same framework is useful to explain all these different phenomena. Talking about the contemporary research about orientation selectivity, it is now more and more believed that the mechanisms underlying orientation selectivity in monkeys and cats are fundamentally different from those mechanisms underlying selectivity in mice. Perhaps we will say a few more things about that when we talk about later in the course when we talk about balance networks. But the framework that we are thinking about is most relevant to monkeys and cats, and very surprisingly also perhaps to flies. So activity in flies, no activity in flies. But this we will leave to the end. Questions? So if there are no questions, I will describe the model. So we are talking about feature selectivity. The idea is that we have, we're looking at the firing rate of neurons as a function of some feature. If we want to be more concrete, we will think about orientation. This is one thing that has been studied more extensively than other things. And when we look at response in the brain, we see something like this. This is the firing rate as a function of this feature. For example, this orientation. Now, as I showed you, we're looking at the voltage sensitive dyes in the primary visual cortex. If this is the response of one neuron, we will also find other neurons that have this response. So they have a very similar response properties, but they are shifted to a different feature. And if you like place cells in the hippocampus, then you can think about this feature as location, and then we have neurons that are most responsive to one point in space, and other neurons that are more responsive to other points in space. Questions? The model we will discuss is called the ring model. And in the ring model, we'll assume that we have a population of neurons, n neurons, and I'm going to plot this population of neurons in the form of a ring. That's why it's called the ring model. Now, I'm not going to argue that we have rings of neurons in the brain. This structure of a ring is in some abstract feature space, and this will be explained shortly. Now, as a spoiler, I'm going to tell you that in the fly, actually, we see this ring. It exists. So there exists a ring of neurons, spatially located ring of neurons. But we're not talking about the fly. We don't care about flies. We're talking about the pinnacle of evolution. We're talking about humans, or maybe cats. And there we don't think, there's no evidence for a ring-like structure. This is a functional description of the model. So we have the n neurons, and each neuron is associated with an angle. So this is neuron I, and it is associated with an angle theta I is equal to 2 pi I over n. And I goes from, let's say, 0 to n-1, or from 1 to n, doesn't really matter. So what do I mean by a ring architecture, or the fact that each neuron is assigned with a particular angle? I mean two things by that. One is that there is something special about the connectivity. There is something special about the connectivity between the neurons, and let me write it here.
Can we maybe denote the neurons as J because we have I inside the theta?
I'm sorry?
Because we have I.
Oh, this I. Actually, some people use J for this I, but I can use J if you want. I don't know. That's whatever. If it makes you happier. No, sorry. Sorry. This is I. This is index. Oh my God. This is index. Index. I is in index.
Should you use J as index?
You want J as an index? Whatever. You want K? Give me a letter. I'll do whatever letter you want. Okay. Connectivity. So what do I mean by neurons that are structured on a ring? I mean that there's something special about the connectivity between the neurons. The connectivity between neuron I and neuron J, the strength of the synapse between neuron I and neuron J, is a function of the difference, absolute value of the difference between these two angles. So the connectivity, for example, between this neuron and this neuron is equal to the connectivity between this neuron and this neuron, or this neuron and this neuron. So there's a symmetry here. Moreover, this implies that the connectivity between neuron I and J is equal to the connectivity between neuron J and I. And we love these models, right? Because we know so many things about symmetric connectivity matrices. specifically, I'm going to consider a particular connectivity function that has the following shape. Jij is equal to 1 over n J0 plus J1 cosine of theta I minus theta j. And we will assume that J0 and J1 are positive. So the implications are the two neurons that are nearby on this imaginary ring, the connectivity between pairs of neurons on these imaginary neurons, the strength of the connectivity is, well, they are connected by excitatory sinuses. However, with respect to neurons that are far away on this ring, connectivity can be either positive or negative depending on the values of J0 and J1. More questions? So one aspect in which these neurons reside on the ring is the structure of the connectivity. Let's write down the equations governing the dynamics. So the dynamics, the dynamical equations are tau Ri dot is equal to minus Ri plus G Hi, where Hi is the input to the neuron, sum over J of Jij Rj plus some external input theta I. So this implies that each neuron receives a different external input that depends on this property of this angle. Where we assume that this external input H0 of theta I is equal to something that is constant to all neurons, H00 plus H10 cosine of theta I minus theta 0. So let's try and understand what's the meaning of this input. We'll assume that H10 is positive, and H00 is positive, and H10 is positive. So what does it mean? One of the neurons here, a neuron whose theta I is equal to theta 0, receives the largest input. Its nearest neighbor neurons receive the second largest input. And the neuron that receives the weakest input in the network would be the one opposite to the one receiving the maximal input. What this model is, what we're trying to model here is the fact that So this term corresponds to external input. So this term corresponds to the selectivity that is due to Hubel and Wiesel, to the Hubel and Wiesel input. So there is some selectivity coming from the outside world, and this corresponds to the input that the neuron receives from other cortical neurons in the network. So what we are trying to model here is the combined effect of the external input and the recurrent connection. So there's a lot of argument in the literature regarding the question of whether we find such connectivity matrix. Much work was done on primary visual cortex. And I think that there is what I would say overwhelming evidence that the recurrent connections have the recurrent connections depend on the selectivity of neurons. For example, neurons that are more closely neurons that are selective to similar orientation are also more strongly connected with each other with excitatory connections. With respect to the specific structure of connectivity that we assumed here, which implies short-term excitation and long-term inhibition, that's less clear whether this is indeed something that we see in the cortex. Questions? The last thing that we need to do in order to define the model is to decide which non-linearity function to use. And the non-linearity that we will use is called the Threshold Non-Linearity. This is g of x is equal to x if x is larger than 0 or 0 otherwise. It's also denoted this way. So this is the threshold linearity function. So this is a model. So from here, everything is just technicality. Basically, everything from here is just technicality. So what kind of question do you think are worthwhile asking in this model?
Fixed point of the model.
Fixed point of the model. What is it that you'd like to explain using the fixed point of the model? I'm sorry?
The behavior is defined.
Okay, so what kind? I see that I ran out of, the battery is dead, so no point using it. So you will just be able to see me but not hear me. Okay, what do you mean by behavior?
And we look at the model, we define, like we look at the integrating model, look what behavior the connection defines.
Okay, so let's start with the simplest version of this model. Let's say that J0 and J1 are equal to 0. right? That would be the easiest. So this would imply that lateral connections have basically no role here. So what kind of behavior would we expect from this model? So again, let's consider the case of J0 and J1 being equal to 0. This implies that the neurons are basically disconnected. So what kind of behavior do we expect to see here? So let's say that the input, this is external, so the external input is theta 0. That would be like the, again, thinking about orientation, this would be the orientation. So what do we expect to see? So let's look at the equations. So this term is, well, equal to 0. Yes?
The output of the neurons, their strength would be depend on theta, and the more closer theta I is to theta 0, the output will be more strong.
Right, so let's look at these equations. So this term is equal to 0. So basically, neurons, looking at this equation, the fixed point is Ri is equal to G of Hi. Hi is just equal to H0 of theta I. So the neuron whose theta I is equal to theta 0 will respond with a fine range that is equal to H00 plus H10. Neurons that are nearby will respond less vigorously to this input. A neuron that has exactly the opposite theta I, that is theta I that is equal to theta 0 plus pi, their response would be H00 minus H10, because this cosine term would be equal to minus 1. Right? Well, not exactly. I was lying because I was assuming that this term is positive. Now, this is a threshold linear function, so it could be if H00 minus H10 is negative, then this neuron would be just, the output of this neuron would be just 0, equal to 0. But other than this small lie, I'm okay. Another small lie another inaccuracy, if you like, another small cheating here in what I wrote. I'm talking about orientation.
Theta is always greater than theta 0.
Why? Let's say theta 0, let's say, is equal to, I don't know, 30 degrees. So theta I can be 20 degrees or 40 degrees. Sorry?
That's the vertical.
Yeah, so let's say that this is an orientation. I'm going to rotate it by 180 degrees. I get exactly the same orientation, right? Here, to get exactly the same orientation, I need to rotate it by 360 degrees. Well, this is a small lie for two reasons. One is if you push me, then I say, okay, actually I'm not doing orientation selectivity, I'm doing direction selectivity in motor cortex, right? That's one way out. Or another would be to say, look, I'm going to do it with this symmetry, and it's actually pretty straightforward. Once you understand this model, it's straightforward to understand how to come up with a model that has 180 symmetry of pi and not for rotation by pi, not by 2 pi. Yes.
You have to multiply the theta I minus theta j by 2.
Yeah. Basically, everything would be to multiply by 2, and so it's not a big deal. So I'm not going to worry about this. And finally, I would say, actually, if we look at the primary visual cortex, it turns out that many neurons are in fact more selective to direction. So they will respond differently to direction in this direction, to movement in this direction rather to movement in this direction. So maybe it's all even okay for the primary visual cortex. But the bottom line is, once you understand this, it's very easy to do true orientation. More questions? Okay. Another assumption that I'm going to make here and this is something that we often do when we study large brain structures like the cortex, is that the number of neurons is large. So I'm going to assume that n is large. What is the advantage of using the large n limit? I'm sorry?
Integrating and understanding the
Yeah, so if we take the large n limit, then this sum becomes an integral. So let's write the equations. So the equation would be r dot. So now, rather than talking about Ri of t, this is what we had previously, we now talk about R of theta in t. So the I becomes theta. So we're taking the continuum limit, and this differential equation becomes, well, let's look at the input. So hi of t also becomes h of theta and t. So we have here two terms. Let's look at the second term first, because it's easier. So h0 theta I will become equal to h00 plus h10 cosine of theta minus theta 0. So I can take whatever theta 0 that I want, just for simplifying the notations. I'm going to assume that theta 0 is equal to 0. You can always change the indices such that theta 0 is equal to 0. So here, the external input would be just equal to h00 plus h10 cosine of theta. Should have been theta minus theta 0. I'm taking theta 0 to be equal to 1. And what do I do with this sum? So the sum would become an integral. It would be an integral over all the angles of d theta prime over 2 pi j0 plus j1 cosine of theta minus theta prime r theta prime, and then we just deleted h00 plus h10 cosine of external input. This is modulation of the external input by a stimulus. This is a contribution of the recurrent connections. And we have the equation of R dot theta and T. Theta T is equal to minus R theta and T plus H theta and T. Is it clear to everyone how I moved from the sum to the integral? Any questions about this? This is a common trick. Basically, we had an average. We had 1 over n here, sum over n terms. This was average over all elements in the discrete space. Now we have integral over the 2 pi angles, an average of these two. This is a good, so from here everything is again, now we just need to solve it and we are done. All the biological assumptions are in this equation. So all the interesting part, if you like, if you're interested in the brain, is in writing this set of equations. And what we will do on Thursday, we will solve these equations. And then we'll be able to learn the role of external inputs, the role of recurrent connections in the behavior of this model. Before I forget, did you receive the lecture notes, the new version of the lecture notes for chapter 1? Okay. We're a bit slow, it's more work than we anticipated, but hopefully we'll soon get chapter 2, the working memory. And again, comments are always welcome.
זה, בהגדרה זה זווית. השאלה זה כאילו מה הקשר בין V לתטא.